So my dear student friends, welcome back to my fourth module. Continuing the previous class, we have discussed already about the fluxes, how to calculate the flux. There we discussed about the two types of fluxes. One we called as a n-type flux, that is with stationary frame of coordinates, and the other flux what we said is the j-type flux, which is relative to the some sort of a relative velocity. Maybe it is based on the molar average velocity or maybe a mass average velocity. So, and for the design purposes we are going to use the n-type flux, and that is with respect to stationary coordinates, and the j-type flux will give you the capability of a species to move from one location to the other location. So, as by this time now you understand there is a relationship existing between the j-type flux as well as the concentration gradient, and one of the famous equation which is known as the Fick's equation, Fick's law. Fick's law is given by a person called Fick in 1885, and what we said, the molar flux of a species related to the observer is moving with the molar average velocity is given by Ja, and which is proportional to the dCA by dZ, where the proportionality constant Ja is equal to minus dAb into dCA by dZ. And if one can notice this equation, and this sort of equation already you came across, and that is nothing but your Fourier's law of heat conduction, or maybe a Newton's law equation, and there by using a Fourier's law of heat conduction one can calculate Q is equal to minus K into dt by dx, and your Newton's law of equation tau x is equal to minus mu into dvx by dv. So I think now by this time you understood what are the three transport processes in chemical engineering, that is the momentum transfer, heat transfer and mass transfer, and you already know about the momentum transfer and heat transfer. Now the next transfer, that is what we are discussing in this semester, is the mass transfer. So where the mass transfer Ja is equal to minus dAb into dZ. So where the dAb is the diffusivity or diffusion coefficient, and this dAb is given by meter square per second, and dCA by dZ is nothing but concentration gradient, and the negative sign indicates generally the fluxes are taken as a positive. dCA by dZ generally in general moving from higher concentration to the lower concentration, so dCA by dZ is going to become negative. To make it J as positive, the negative sign is incorporated here, so the flux is equal to Ja into minus dA by dAb into dCA by dZ. And by this time you understood, as I told you, there are relevant equations in the heat transfer as well as the momentum transfer. So if one can understand the what do you call it as heat flux, heat transfer or maybe momentum transfer, so you can have the analogy with the mass transfer process, so you can estimate the mass transfer flux. And now we can discuss something like what is happening. Like for example, if you see there is a box, and this box is partitioned by two walls, and here we are going to take 100 kgs of water, and here we are going to take 100 kgs of ethanol. So when you take 100 kgs of water and 100 kgs of ethanol, these two are separated by a partition, and because the densities of the water and ethanol are two different things, so we are keeping the partition in such a way that the volume of this chamber and the volume of this chambers may be some sort of equal. So now what one can do, we can remove the partition. When you remove the partition, obviously there is the concentration gradient for the water from this side to this side. For the ethanol there is a concentration gradient from the this side to this side. So what will happen now? The ethanol is going to move from this direction to this direction, water is going to move from this direction to this direction. Ultimately the system is coming into the uniform concentration. So when the system comes to the uniform concentration, what one can expect, there is a 50% concentration throughout the chambers. So now you can see initially the depths are adjusted in such a way that depths are adjusted. So now after end of the process, if you can see, there are 44.08 kgs of water here and 44.08 kgs of ethanol, and whereas when you talk about here 55.92 kgs of water and 55.92 kgs of ethanol. So that means the system is initially, even though it is a knife edged initially, and at the end of the process, if you see, it is moving on the right side. So what is happening here? And that means there is a flux of A, that is a water flux in this direction, there is ethanol flux in this direction, and there is a net flux N is equal to Na plus Nb. So if you take Na is a positive, obviously the Nb is going to become say negative, and to obtain a relationship between to calculate this flux of Na, what one can see, you know that U is equal to, that is nothing but a molar average velocity, U is equal to 1 by C into sigma of Ci into Ui, sigma of Ci into Ui. In this case, we are talking about a binary system. There are two components are there, component A and component B. So it is going to become 1 by C, Ca Ua plus Cb Ub. And according to our definition, it is going to become 1 by C is equal into Na plus Nb. And at the same time, what one can see, your Ja is equal to, already we have written Ja is equal to minus dAb into dCa by dZ. This is also equivalent with the Ca into Ua minus U. Then this can be written as Ca Ua Ca into U, and this Ca into Ua, as you know, this is nothing but Na minus Ca by C. You substituting the this particular expression in this equation, this is going to become Na plus Nb, or your Na is equal to Ja plus Ca by C into Na plus Nb. So the flux of species I is equal to a diffusion flux that is occurring because of the molecular diffusion, and this is nothing but a total flux, what we call it as the bulk motion. This is due to the bulk motion, and this is the diffusion flux. So that means when you remove the partition here, and suddenly there is a bulk movement of the water from the water side to the ethanol side, and at the same time ethanol side to the ethanol is flowing from the ethanol side to the water side, and at the same time there is some molecular motion because of the concentration gradient. Water is moving from this side to this side, ethanol is moving from the this side to this side. So in every case we are going to come across two terms when you are going to calculate the total flux, and the total flux is nothing but a diffusion flux as well as the flux due to the bulk motion. And similarly one can write it for Nb is equal to Jb plus Cb by C into Na plus Nb. That is nothing but, if you can add these two equations, so one can prove that Ja is equal to minus Jb, or it is going to become minus Dab into dCa by dZ is equal to minus dBA into dCa by dCb by dZ. And if total concentration C is equal to Ca plus Cb is equal to constant, then dCa by dZ is equal to minus dC by dZ. So dAb is equal to dBA. dAb is equal to dBA. Then sometimes the diffusivity, that is the diffusion coefficient, which may be varying in the direction. If the diffusivity is varying in the direction, then we call it as the anisotropic materials, or the otherwise we call it as a isotropic materials. Anisotropic materials. In this case, diffusivity is not varying as a function of direction, whereas we call it as the isotropic, where in this case the diffusivity is not going to vary as a function of direction. And we define another thing, that is what we call it as the diffusional velocity. This is the relative velocity of the molecular species with respect to an observer moving with the average velocity, and this is given by V into VAD is equal to UA minus U, that is equal to JA by CA, that is equal to DAB by CA into DCA by DZ. So this is what now the question comes here, why should I calculate the flux? And that we will discuss at a later stage when we are discussing about calculations of the flux NA. Now we will derive another important equation. That equation is known as the equation of continuity, and this equation of continuity already you might have seen in the fluid mechanics, where we derive equation of continuity as well as the equation of motion. But from the point of when we are working with the mass transfer, there one species is not moving, two species are moving, maybe in the same direction, maybe in the other direction. So what one has to understand, you should know how to calculate the equation of continuity, where this equation of continuity is obtained by making your law of conservation of mass, or what we say your mass balance equation. So in this case, what we can do, we have a three-dimensional system, where in the three-dimensional system, so here we have a one point, this is the another point, maybe you can call this is the x, y, z point, and this we can call it as a x plus delta x, y plus delta y, z plus delta z. This is the x coordinate, this is the z coordinate, this is the y coordinate, and you can see this is nothing but your delta x thickness, this is nothing but your delta y thickness, this is the delta z thickness. So what we are doing is we are taking some cubic volume, we are taking a volume element which is a cube, where the coordinates are it is having a thickness of delta x in the x direction, delta y in the y direction, and delta z in the z direction. So what we can do, so now the mass is some mass is entering from all three directions, so x direction as well as the y direction and z direction, and similarly the mass is going to leave in the x direction, y direction and the z direction, and at the same time when mass enters and leaves, there if the system is an unsteady state system, there is an accumulation of mass within the cube. Then and at the same time when the reaction when the molecules enters into the system, it may undergo some chemical reaction, and when it undergoes a chemical reaction, so there is a consumption or the formation of the molecules of A. So what one can do, we can write is mass in, mass out plus rate of generation or consumption, this will write it as a negative sign, that is equal to rate of accumulation. So now what we can do is how much of mass that is entering into this cubical system and how much of mass that is leaving from the cubical system, and if one can say, one can know how much of mass that is generating or consuming in the system. Then at the same time, if you know the rate of accumulation, if we can make this overall balance equation, one can get the equation of continuity. So now, as I told you, the mass is entering from the x direction, the mass is entering from the y direction, the mass is also entering from the z direction, and at the same time the mass is leaving and x direction, y direction as well as the z direction. So now the mass in, mass rate of flow of component A, that is equal to NAx, where x indicates the x direction flux, and where x indicates it is entering at x. Then this is the molar flux. To make it as a mass flux, we are going to multiply with the molecular weight. So molar flux multiplied by molecular weight entering at a point x and in the x direction, entering at a point x in the x direction, and this is the molar flux. And when you want to have a molar mass flow rate, one has to be multiplied with the molecular weight as well as the area perpendicular to the flow. When you talk about the x direction, the area perpendicular to the flow is the y direction as well as the z direction. So what we can do, we can multiply with the area, that the area of the area is nothing but delta y plus delta z. Similarly, you can write it for the NA y in the y, entering at y, delta y, delta z, that is the flux entering along in the direction y direction, and that is multiplied by the area perpendicular to the flow, and NAZ entering at z, delta x, delta y. This is the mass rate of flow of component A, and the mass rate of flow of component, flow of component leaving, mass rate of flow of component A entering, this is nothing but leaving. So when you talk about the leaving, this is again NA x. Now it is nothing but x plus delta x, where because this is the leaving at x plus delta x. Again there will be, sorry, here there will be MA, there will be MA, and x plus delta x, MA, delta y, delta z, NA y, y plus delta y, delta y, delta z into MA, NAZ at z plus delta z, MA delta x to delta y. So this is the mass entering, this is the mass leaving, and A is generated, I mean there will be accumulation, and that accumulation can be calculated. So volume element is nothing but delta x, delta y, delta z, and when you calculate a mass, volume multiplied by density, that is nothing but delta x, delta y, delta z into rho A. When you want to calculate the accumulation, it is going to become delta x, delta y, delta z, dou rho A by dou T, where whenever you are talking about accumulation, the term of T is going to be appears. Then this is the accumulation term. Then the next thing is rate of generation. Some amount of A is entering. A may be some amount of A is going to participate in the chemical reaction, and if you say RA is rate of formation of A multiplied by MA, that is nothing but this is the molar rate multiplied by molecular weight into delta x into delta y into delta z. Now substituting all these four things in the mass in, mass out, plus or minus rate of generation or a consumption, rate of accumulation, if you can substitute these terms into this equation, here NAX at x, MA delta y, delta z, x plus delta x, minus NAX at x, MA delta y, delta z. This is for the x direction. Similarly, for the y direction, what we can write, NA y, y plus delta y, MA delta y, delta z, delta x. So this is delta x and this is delta x, delta z, delta x minus NA y, y, MA delta z, delta x plus NA z, z plus delta y, MA into delta x, delta y, NA y, at y NAZ at z delta x delta y plus MA RA MA into delta x delta y delta z, that is equal to delta x delta y delta z dou rho A by, now dividing with delta x delta y delta z and taking delta x tends to 0, delta y tends to 0, delta z tends to 0, that we are taking a differential, the thickness, the differential thicknesses are becoming into 0, and here this is going to becomes NAX at x plus delta x, NAX at x divided by delta x whole multiplied by MA plus NAY y plus delta y minus NAY at y delta y plus NAZ z plus delta z minus NAZ z divided by delta z whole multiplied by RA into MA, that is equal to dou A rho A by dou T. And when delta tends to delta x tends to 0, delta y tends to 0, limit delta tends to 0. This is nothing but f of x plus delta x minus f of x divided by delta x. This is going to becomes MA dNAX by dx, MA into dNBX dNAY by dy, MA into dNAZ by dz plus RA into MA is equal to dou rho by dou T. Similarly, for component B, one can write it as MB dou NB x by dou x, MB dou NB dou y, MB dou NBZ divided by dou z plus RB into MB dou rho A by dou rho B by dou T. So this is the mass balance equation, or the for a component A, this is the mass balance equation for the component B. Now if you add these two in the volume element, whatever you are talking about, the A molecules are entering, or the A is reacting producing B, and B is reacting and producing A. That means how much of mass of A is disappeared, appeared, the same amount of mass of B is disappeared. That means your RA into MA is equal to RB into MB. And when you add these two equations, this is going to becomes dou by dou x MA NAX plus MB NBX by dou x plus dou by dou I of MA NB NAY plus MB NBY plus dou by dou z of MA NA Z plus MB into NBZ plus these two terms are going to be cancelled. Then we are going to have dou by dou T of rho A plus rho B, that is nothing but dou rho. But as we discussed earlier, we have written equation for NAX, and we have written for the, we know what is the flux of A in the x direction plus flux of B in the direction, and that can be written as dou by dou x of rho ux plus dou by dou y of rho uy and dou by dou z of rho uz is equal to dou rho by dou t. Now, if you can expand this expression in the UV product formula and bring all the velocities on one direction, one side, all the densities on the other side, it is going to become rho into dou ux by dou x, dou by dou y uy plus dou uz by dou z into rho, that is equal to ux dou rho by dou x plus uy dou rho by dou y plus uz dou rho by dou z negative plus dou rho by dou t. This is what we call it as the equation of continuity. Now, suppose if the system is a constant density, this rho is not going to vary as a function of x, rho is not going to vary as a function of y, rho is not going to vary as a function of z, and rho is not going to vary with respect to time. Then it is going to become dou ux by dou y dou x, dou ux by dou x plus dou uy by dou y, dou uz by dou z, that is equal to 0. And this is the special form of equation of continuity that you have studied in the fluid mechanics. Then one can write, taking a metal balance equation for the component A, and if you can simplify, one can show that we are going to get the equation, fixed second law equation, that is equal to dou Ca by dou T is equal to dAB into dou square Ca by dou x square plus dou square Ca by dou y square plus dou square Ca by dou z square. This is similar to your second Fourier's law of heat conduction. This is what we call it as a second fixed law equation, right? And now this is the equation of continuity, and this equation of continuity we are going to use it whenever we are going to write the mass balance equation, or when the mass is produced and when the mass is reacted or the mass is produced. So we can use the general form of equation of continuity or the special form of equation of continuity, whether the constant density system or not. Based on that we are going to get this expression, and this is the fixed second law equation. This we are going to use it when you are talking about unsteady state systems. So this is what we are going to study in the later stage when you are working with the unsteady state diffusion through the solids. We can use this expression to calculate the concentration profile as a function of time as well as the function of concentration. So this equations is clearly indicates to you how much important that mathematics is there for chemical engineering. It's not only for the chemical engineering, even other branches of engineering one should know about the mathematics, and without mathematics nothing can be done. We are interested to estimate the steady state molecular diffusion in fluids. As already we have known, your Na is equal to Na plus Nb into Ca by C plus Ja, that is equal to Na plus Nb into Ca by C minus Dab into Dca by Dz, substituting the fixed second law equation. Now Na minus Na plus Nb Ca by C, that is equal to dAB into dCA by dZ. This is going to become negative sign. Now dZ Z1 to Z2, that is equal to integration of minus C dAB into dCA divided by NA NAC minus NA plus NB into CA, where CA1 and CA2. And if you integrate if you evaluate this expression, this is going to become this, and on the other side we are going to get Z by C into dAB, assuming that the total concentration, the diffusivity is generally a function of concentration. If you can assume that dAB is not a function of concentration and the concentration is not going to vary, the total concentration is constant, so one can write this. Or if you can multiply Na on both sides, this is going to become Na by Na plus Nb C into dAB by Z ln of Na into C Ca2 Na plus Nb divided by NaC Ca1 Na plus Nb. This is the most important expression. One can calculate the flux, and if you can look at the equation, this side we have a flux and the other side also we have a flux, and we have a flux of component B, and solving this equation is not so simple. And what one has to know, we have to know the relationship between the Na and Nb. Once if you know the relationship between the Na and Nb, then one can calculate the flux. So what we can do, we can discuss about some special cases, and initially what we can do, we can work out gases separately and we can work out for liquids separately, then we can discuss about some special cases. And here you can see, right, many of you may know or many of you may not understand why do you need to have a flux, where flux is equal to kg moles per meter square per second, and unless and otherwise we don't know about this value, one cannot do the design. A simple example, when you can look at your bathroom, we may be using some Vodanil for the bathroom freshener, and when you keep your Vodanil in a bathroom freshener, and some amount of the material, that Vodanil, is continuously dissolving into the air, and slowly quantity it is going to be decreasing. So one should know when I have to purchase the new Vodanil. If I have to know that when I have to purchase the new Vodanil, you know the room area, that is nothing but area is known, and you know flux, that is the flux we are going to calculate from this equation, and we know the flux, we know the area, we can find out time, and the time will gives you when we have to replace the new Vodanil. So this is the simplest example I am trying to give you, but when you go to the industry, we are going to find out several of such type of examples. Unless otherwise we don't know the value of Na, one cannot proceed further. So when one cannot do any design of a mass transfer operation unit or any separation process. So we are now looking at diffusion, molecular diffusion through the gases. Molecular diffusion. So molecular diffusion in gases, when you talk about the gases, you know, for if the gas obeys the ideal gas law, one can apply the simple equation of state. I think all of you know what is the equation of state. Equation of state is the equation which gives the relationship between pressure, volume and temperature. And one of the simplest equation of state that is known to us is the ideal gas equation, where the ideal gas equation PV is equal to nRT. And if you look at this equation, and if you want to calculate N by V is equal to P by RT, where N is the number of moles and V is the volume, that is nothing but your molar concentration, and this molar concentration C is equal to PT by RT. And for a component A, this is going to become Ca, that is equal to Pa, that is the partial pressure of component A, RT. So when you are working with the gaseous systems, the concentrations can be written in terms of a partial pressures. So when you write in terms of partial pressures, you are now, this expression is going to become Na by Na plus Nb Pt by RT dAb into Z ln of Na Pt minus Pa2 Na plus Nb, Na into Pt, Pa1, Na plus Nb. So when you are working with the gaseous systems, the concentration can be replaced with respect to partial pressures and the total pressures. So you can write this expression, and even if you look at the equation, we have to know the relationship between the Na and Nb. Unless and otherwise we don't know the relationship between Na and Nb, one cannot evaluate this, one cannot calculate the flux, and the relationship can be established between the Na and Nb by knowing about situations. For example, if you look at the methane cracking, as we are discussing yesterday, the methane cracking gives rise to carbon and hydrogen. And when you see this expression, 1 mole of methane is there, that gives you 2 moles of hydrogen. That means I have a catalyst surface, and 1 mole of methane is coming to the catalyst surface and 2 moles of hydrogen is going, and that means your Nb, that is nothing but flux of hydrogen, is equal to 2 times of flux of methane. So now that means you know Na by Na plus Nb is equal to -1. So this is the one way one can establish, once if you know simple, if it is a chemical reaction, when a chemical reaction is taking place, one can establish the relationship between Na and Nb by knowing about the stoichiometric equation. So when you are working with the physical processes like maybe a distillation column, and maybe by knowing about the enthalpy balances, one can estimate the relationship between Nb and Na. So by knowing about the reaction stoichiometry, or by knowing about the physical process where we are working, one can find out the relationship between Nb and Na. So once if you know that relationship between Nb and Na, we can solve this expression, one can get the flux. So as I told you, without the values of flux, one cannot proceed further for the design of any columns. Now we are going to come across 2 simple cases. One simple case is the non-diffusing B case. A through non-diffusing B. In the case of A through non-diffusing B, A is diffusing through a non-diffusing B. For example, when you are working with many of the applications, we need the dry air, but dry air contains some moisture. So there is a necessity to remove the moisture. So this moisture can be removed by exposing to the sulfuric acid, let's say. So we have a sulfuric acid, we have a air, and this air contains the air plus moisture, and when you have the air plus moisture, when you are going to contact these 2 phases, the moisture now will be transferring in from a air phase into the sulfuric acid phase. So now if you look at this whole problem, only one component which is diffusing from gas phase to the liquid phase, no other molecules are moving. And if you can take air as a B molecules, moisture as a molecule, so your Nb is equal to 0 and your Na is equal to some value of Na. So now if that is the case, this is the special case 1, where special case 1 is nothing but A through non-diffusing B. In the case of A through non-diffusing B, A is only diffusing and B is not diffusing. That means your Nb is equal to 0, your Na is equal to some value of Na. And here then we are going to get Na is equal to Pt by Rt dAb by Z ln of Pt minus Pa2 divided by Pt minus Pa1. As all of you know, the total pressure of the system is constant. That means your Pt is equal to Pa1 plus Pb1, that is sum of the partial pressures at a location 1 is equal to total pressure. Similarly, sum of the partial pressures at a location 2, that is a Pa2 plus Pb2, or one can write Pa1 minus Pa2 is equal to Pb2 minus Pb1. Pa1 minus Pa2 is equal to Pb2 minus Pb1, or one can write it as Pa1 minus Pa2 divided by Pb2 minus Pb1, that is equal to 1. So in this expression, what one can do, we can write it as Pt by Rt dAb into Z. We can multiply 1 with the 1, and 1 can be written as from this equation as Pa1 minus Pa2 divided by Pb1 minus Pb2 multiplied by ln of Pb2 by Pb1. Now if you look at this, Pa1 minus Pa2 divided by Pb1 minus Pb2 ln of Pb2 by Pb1, it is called as a Na is equal to DAB by Z into PT by RT into PT by RT, PB ln PA1 minus PA2 divided by PB ln, where PB ln is the logarithmic pressure difference. So once if you know the logarithmic pressure difference, one can calculate the flux, that is the flux of component A, and if one can represent with a graphical fashion, this is the B is decreasing, A is going to be increasing, and a total pressure is going to become a constant. So this may be a distance, this may be a pressure, and this is PB1, maybe this is the PB2, this is the PA1, and this is the PA2, and this is the total pressure PT. So many of the applications we are going to come across in the chemical engineering, one can use this thing and we can calculate it. The special case, another special case is equimolar counter-diffusion. In the equimolar counter-diffusion, for example, if I have some carbon surface and now we have a air film, and here in the air film basically we have a O2, the O2 go to the carbon surface, the reaction is taking place between the carbon and oxygen, there is a formation of CO2. So 1 mole of, if the complete combustion is going to take place, 1 mole of oxygen will provide the 1 mole of carbon dioxide. This oxygen is flowing in the one direction, the carbon dioxide is flowing in the opposite direction, and your Na is equal to now in this case minus Nb. That is what we call it as the equimolar counter-diffusion. If it is going to become the equimolar counter-diffusion, then your Na is equal to simply minus dAb by RT into dPa by dZ, and that is equal to dAb by RTZ PA1 minus PA2. So this is the equation that we are going to use it for the equimolar counter-diffusion. So once if you know either non-diffusing B case or the equimolar counter-diffusion case, so you have expressions, this equation, and we have expression for this equation, one can calculate the flux. Once if you know the flux, other things can be calculated. And this is the one example where we are talking about Na is equal to minus Nb. In some other applications what we can have, when you are working with the distillation column, you may be studying in the next semester. So when you are working with the distillation columns, so 1 mole of more volatile component is coming into the gas phase, and at the same time 1 mole of less volatile component is moving from the gas phase to the liquid phase. So Na is equal to minus Nb, that is comes out to the equimolar counter-diffusion. If that is the case, one can calculate the Na is equal to this expression. So similarly, one can, once if you know the Na, one can calculate the Nb. Now this is for the gaseous systems. When you talk about the liquid systems, generally the liquid systems, the concentration and diffusivity are very strong functions of a location, so one cannot use so simply. But the thing is, when nothing is available, one can assume dAb as well as C is constant, and for the non-diffusing B case, molecular diffusion, for the non-diffusing B case, molecular diffusion in liquids. So we can write it as Na is equal to Na plus Na by Na plus Nb dAb by Z, where instead of Pt we can write it as rho by M average, where rho is the molar density, mass density divided by average molecular weight, ln of Na by Na plus Nb minus Xa2 divided by Na by Na plus Nb minus Xa1. Now suppose when you talk about and where rho and M are the solution density as well as the molecular weight, so one can calculate at point 1 what is the concentration and what is the density, what is the molecular weight. At point 2 what is the concentration, we know, what is the density one can know, and we can calculate the rho by M average. So once if you know the rho by M average, one can calculate the Na. So special case number 1, case number 1, that is nothing but A through non-diffusing B. In the case of A through non-diffusing B case, your Na is equal to dAb by Z into rho by M average is equal to Xa1 minus Xa2 divided by Xb ln. where xB ln is the logarithmic average concentration for component B. And special case 2, equimolar counter diffusion. In this case of equimolar counter diffusion, so we are going to get Na is equal to dAB by Z rho by M average into XA1 minus XA2. So these are the equations that we are going to use for the liquid system. Already we know for the gaseous systems, so one can use these equations for a special cases of non-diffusing P case as well as the equimolar counter diffusion, and one can calculate the fluxes. Now, if we are working with the multi-component systems, and if suppose somebody was working with the multi-component systems, and we are going to come across so many multi-components everywhere, even if you talk about some crude petrol, it contains several of the components, either during the transportation or maybe during the separation process and other things. One has to know how much of flux it is going to be there. So if that is the case, it is not so simple, and one can use the Maxwell's multi-component systems, and one can use the Maxwell-Stephens equations, and these Maxwell-Stephens equations one can use, and one can estimate the multi-component when you are talking about the multi-component fluxes. So we are going to come across these multi-components at several places, and here for a simple case we can use a Maxwell-Stephens case, but in some simple cases, instead of talking about, we are going to call it as a effective diffusivity, what we talk about. And suppose now in this case we are going to replace Na by Na plus Nb is replaced sigma of Ni, and where Ni is the flux of component I, and it is taken as a positive if it is flowing through the same direction in which A is flowing. If it is flowing in the opposite direction, if A is flowing in one direction, if I is flowing in the opposite direction, your Ni can be taken as a negative. That means Ni is a positive if it is flowing in the same direction, if it is flowing in the same direction of A, and it is a negative if it is flowing in the opposite direction. So if it is flowing in the same direction, we are going to take Ni is positive, otherwise we are going to take it as a negative if it is flowing in the opposite direction. And your DAB is replaced as DAM, that is where DAM indicates diffusion coefficient of A through a multi-component mixer, or we call it as a effective diffusion coefficient. And this effective diffusion coefficient DAM can be written as Na minus Ya sigma of Ni divided by sigma of 1 by dai Ya Ni Ni, here I is equal to 1 to N, I is equal to A to N. So if you know the fluxes of component A, component B, component C, component N, one can substitute all the things in this expression, and one can calculate the effective diffusion coefficient. And once if you know the effective diffusion coefficient, we can use the same expressions whatever we have discussed earlier for the non-diffusing B case and equimolar counter diffusion. Instead of DAB, we can substitute as a DAM, and we can solve this equation. And now a common situation that we are going to come across, all N's, all Ni's except N A are 0. That means your Na is equal to Na, there is a value of Na, Nb is equal to Nc is equal to Nd is equal to N, Z is equal to, that is going to become 0. If that is the case, we are going to write DAM, effective diffusion coefficient, 1 minus Ya by sigma of Ya by dAi, where I is equal to B to N, and this is written as 1 by sigma of Yi prime by dAi, where I is equal to B to N, and where this Yi prime is contains the molar ratio or mole fractions calculated assuming that on A free basis. Mole fractions are calculated on mole free basis. So on A free basis one can calculate the DAM once if you know the DAM, and you can use the previous equations and one can calculate. So this is the what I want to talk about with you in this class. And basically what we have discussed here, we have discussed about what is the Fick's law and how the Fick's law is analogous to your Fourier's law of heat conduction as well as the Newton's law. Then we have discussed about the equation of continuity. Then we have discussed about the estimations of the fluxes and when the flow is in a laminar flow, assuming that DAB is constant, and when we want to calculate the fluxes, so we should know the relationship between the NA and NB. This relationship between NA and NB can be obtained once if you know the stoichiometric equation if the chemical reaction is taking place, or it may be obtained from the physical processes if you know about some sort of enthalpy balance equations. And we have two special cases, that is nothing but A through non-diffusing B and molar counter diffusion, and we have a simplified expression. And when you are working with the multi-component systems, instead of using a simple diffusion coefficient, we are going to use the effective diffusion coefficients, and these effective diffusion coefficients we are going to use for the calculations of the fluxes. So when we meet in the next class, we will solve some problems related to these equations. So I request all of you to go through your material seriously and be ready for the next class where we are going to solve some numerical problems related to this.